So next we look at moment generating functions, and it's interestingly, I have a playlist on moment generating functions. I did that a long time ago. You want to come to my channel, you okay, and just scroll down to that place to see moment generating functions. Okay, where is it now? Moment generating function. Oh, yeah, it's okay. I have generating functions in general, not just moment generating functions. Yeah, I have generating functions. I think 20 videos and also definitely you're going to come across the idea of moment generating functions right there. If you check, yeah, moment calculation from PGFs, all of that. You have all that there. So it gets, I mean, it's mostly statistical, right? And we have its application in cryptography, data science, and all of these things. So you want to check that out too. But then, of course, we are reviewing these concepts as we lay foundations for, as we lay foundation for stochastic processes. So, moment generating functions, MGFs, are important tools in probability theory and statistics. They encode the moments of a random variable into a single function and are useful for computing moments such as mean and variance. So, mean and variance are moments, right? So, identifying probability distributions, studying sums of independent random variables, and providing theoretical results such as the central limit theorem, which we are going to consider in a future video, maybe the next video or the one after that. So, if the moment generating function of a random variable exists in an open interval and around zero, it uniquely determines the distribution. So let's look at the definition of moment generating function. So for a random variable big X, the moment generating function MGF is defined as m sub x of t equals the expectation of e raised to power tx, where e dot denotes expectation, like I said, and t is a real parameter, while x is a random variable. So the MGF summarizes all the moments of the distribution of x. So now, if you look at the MGF moment generating function for random variables now. If x is a discrete random variable with probability mass function p of x equals x, then the m sub x of t equals expectation over x of e raised power tx multiplied by the probability that x is equal to x. This means we multiply each value of the random variable e raised power tx and then take the expected value. So MGF for continuous random variables now. If x is a continuous random variable with probability density function f of x, then m sub x of t is summation from minus infinity to infinity of e raised power tx f of x dx. This integral computes the expected value of e raised power tx. Why it is called moment generating? Why do we say a moment MGF? Why do we call this a moment generating function? So the derivatives of the MGF evaluated at t equals 0 generate the moments of the distribution. So the nth moment is the expectation of x raised power n, and that is m sub x raised power n of 0. And this means that the expected value of x raised power n is the nth derivative, that's the n the tn of mx of t evaluated at t equals 0. Thus, the MGF can produce all moments of the distribution. Okay, so if you need the second moment, just put 2. If you need this first moment, differentiate once, and so on and so forth. So important special cases which we are going to look at now. So imagine for the mean, right? The expected expectation of x is the mean is the expression of x, right? And that is m sub x prime. That's first derivative of m of x evaluated at 0. And second moment, uh, which is connected to variance. It is not directly variance, but second, you need second moment and first moment to generate variance. So expected value of x, where that's second derivative of the moment generating function evaluated at 0, such that you can now get variance to be variance of x equals expected value of x squared, which you got here, minus expected value of x, which already got as raised to power 2. So using MGFs, this becomes that the variance of x is the second moment minus the square of the first moment, basically. So looking at that for some distributions now, let's start with a Bernoulli distribution. Suppose x is a Bernoulli random variable, where we have probability that x is equal to 1. Let's say that is p. So a Bernoulli situation is like when you have if success and failure kind of situation. So if it's either something succeeds or it doesn't succeed, something happens or it doesn't happen. So probability that x equals 1 is p, probability that x is equals 0 is 1 minus p, for instance. So the moment generating function in that case can now be m sub x of t equals the expected value of e raised to power tx. And that, so using the definition, we know that that is mx of t equals e raised to power tp plus 1 is 1 minus p. Therefore, mx of t is 1 minus p plus p e raised to power t. Well, in case you're wondering what exactly is happening, so that's p of x equals 1. That's probability that x is equal to 1 is p, and probability that x is equal to 0 is 1 minus p. And we are looking for the moment generating function mx of t, which is equal to expected value of e raised to power t x. So how do we handle this now? We know that m sub x of t will have to be something like this. So for each one now, so we have, first of all, you have x for this, we have two parts. We have this part and this second part now. So it's more like you have so you have e raised to power the expectation of t, the expectation of e raised to power t x1, if you like, right? Plus the expectation of e raised to power plus the expectation of e raised to power t x2, tx2, like this. So that means you multiply each one by its probability. So the probability of x1 in this case will have to be p, that's that p, multiplied by e raised to power t. X1 is actually 1. So you have p into e raised to power t multiplied by 1, plus the expectation that's the probability itself is 1 minus p multiplied by the variable, that's e raised to power t. X2 is actually 0. This is, if you call this x1 and you call this one x2, if in that sense, so that is 0. So that you now have p e raised to power t plus 1 minus p e raised to power t raised to power t 0 is t times 0 is 0. So you have p e raised to power t plus 1 minus p, multiplied by 1, like that. So you have pe raised to power t plus 1 minus p. And that is exactly what we get over there. So in that case, you have 1 minus p plus p e raised to power t. So to get the mean from this case now, to get the mean, we differentiate the MGF once, because the mean is the first moment. So we have mx sub t, mx prime, that's differentiate once, and you get p e raised to power t. If you evaluate at t equals 0, you just get p. So for mean, in short, we are saying that for the mean, so this is mx sub t right here. This is m sub x of t, rather. So for the mean, what do? We say that we differentiate, right? So we have m sub x prime of t. That's differentiate once. So this one has no t, so it crosses out automatically. So we just have, when you differentiate e raised to power t, you get e raised to power t. So that's p e raised to power t. So at t, you have to evaluate at t equals 0. So at t equals 0, we have mx prime at 0. That is p e raised to power 0, which is p times 1, and that is simply p. So the mean for Bernoulli is simply p, like that. Okay, so we can also go ahead and do for variance and all of that. So for the variance from Bernoulli moment generating function, so you differentiate the second time. Of course, if you differentiate p e raised to power t the second time, you get p e raised to power t, because e raised to power t never dies, right? Never changes. So evaluating at t again, you still have p. So it tells you that the variance x, you remember that the variance of x is the expectation of x squared. What you have evaluated now, where expectation of x squared, that's this evaluated at 0, that will give you p. So you have p minus p squared. So the variance is p into 1 minus p for Bernoulli. And then we can do the same thing for Poisson distribution. So let x be a Poisson distribution with parameter lambda. Okay, the probability mass function. In fact, we saw this already when we did the introduction to stochastic processes. We are still going to see it when we get to Q theory, because the parameter lambda would usually represent arrival rates on a queue. So the probability mass function here is probability that x equals e raised to power minus lambda multiplied by lambda raised to power x all over x factorial. So deriving the Poisson moment generating function. So you have m sub x of t equals expectation of e raised power tx. And again, we have the whole summation. Summation from x equals 0 to infinity of e raised power tx. All right, e raised power minus lambda, lambda x all over x prime. Okay, and what do? You take the x's one after the other. So when x is 0, right, you have e raised power when x is 0. Okay, well, we can even still tidy things up a little bit. So bring out the constant, which is e raised power minus lambda, for instance. And then this lambda is raised power x, so you can still leave it. So now you have summation from x equals 0 to infinity, lambda e raised power t, all raised power x all over x factorial. So this whole expression now looks like you have, if you use the exponential series, so this whole thing looks like you are dealing, so the summation from x equals 0 to infinity of any a raised power x over x factorial would usually be given as e raised power a, right? So e raised power a. So mx of t is like you have e raised power minus lambda multiplied by e raised power lambda e raised power t. E raised power lambda e raised power t. So mx of t is now the exponent of lambda. It's like you put these two together now. So you have lambda e raised power t minus lambda. That's lambda into e raised power t minus 1, like that. So you can then do mean, variance, and all of that. So the mean and variance of Poisson. So the mean, for instance, you differentiate this once, and if you evaluate at 0, you get lambda. Second derivative also gives us that variance of x is also lambda for Poisson. So if you try it for exponential distribution, so if x follows exponential distribution with parameter lambda, the probability density function is f of x equals lambda e raised power minus lambda x as x for x greater than 0. So you can then derive the exponential MGF. So that's expectation of e raised power tx. That means e raised power tx multiplied by the function itself. That's lambda e raised power minus lambda x. So if you integrate all that over from 0 to infinity, you get the moment generating function m sub x of t to be lambda over lambda minus t. So for t less than lambda in that case, so you can then find, so of course, to find the mean, differentiate this once. When you differentiate this once, should I try that? Okay, I think let me just try this. I've been skipping the other ones. So let me say mx of t equals lambda over lambda minus t. So that is for, is it exponential distribution, right? Exponential distribution, yeah. Exponential distribution. Exponential distribution. So we have m sub x of t to be lambda over lambda minus t. Lambda, that's lambda over lambda minus t. So we can also write it like lambda into lambda minus t, like this, raised power minus 1. Or we can do quotient rule if we like. So for mean now, so we say for mean, we need m sub x prime of t. That's differentiate once. So this is constant. So we have this constant here multiplied by, to differentiate this component, bring down the power, that's minus 1. Then differentiate inside that with respect to t. That's differentiate minus t with respect to t, you get minus 1 again. Differentiate minus t, you get minus 1. Then you now have lambda minus t raised by minus 2, because you reduce the power of that by 1. So this is now minus and minus is plus. So you have lambda over lambda minus t all squared. So you now do m sub x prime evaluated at time 0. Okay, that is lambda over lambda minus lambda all over lambda minus 0 squared. So that is lambda over lambda squared. So that is lambda over lambda squared. And that is 1 over lambda. Okay, is that the mean actually? The mean here, yeah, okay. The mean is 1 over lambda. 1 over lambda, yeah, because lambda over lambda squared is 1 over lambda. So we say the expected value of x, the expected value of x is 1 over lambda for the exponential distribution. So for variance, so if you're going for variance, so for variance, we get we need m x prime prime of t. So already we already have mx prime of t, which is what we got here now. That's lambda over lambda minus t all squared. So that's so we need to differentiate. So that's d dt of lambda all over lambda minus t all squared. That's like we're differentiating the second time. So lambda over lambda minus t all squared. So that's like d dt of so that's lambda. I like to make it one expression like this for easier handling. So again, this is d dt. Oh, okay. Yeah. So to differentiate now, we can keep this. So lambda now into bring down the power again. Then differentiate inside. That's -1. Then reduce the power. That's lambda minus t raised by -3. So that mx prime prime of t now is equal to minus 10 -1 is 2. So you have 2 lambda all over lambda minus t raised by -3. Raised by 3 actually. I hope I did that well. Yeah, I think that works. Raised power 3. Okay, so now we have mx prime prime evaluated at 0. That is 2 over lambda all over lambda minus 0 raised power 3. That is 2 lambda all over lambda cube. That is 2 over lambda squared. So now 2 over lambda squared is the second moment, and it is the same thing as expected value of x squared. So to get the variance, so we know the variance of x is equal to expected value of x squared minus expected value of x all squared. So expected value of x squared, which we got now, is 2 over lambda squared. Expected value of x that we already got before was 1 over lambda. So this we have 1 over lambda all squared now. So that means we have 2 over lambda squared minus 1 over lambda squared like this. So that means we have lambda squared, that's 2 minus 1, so which is 1 all over lambda squared. So again, we have the variance of x. Variance of x now is 1 over lambda squared. The mean is 1 over x, like we already got before now. So this is the mean, like that. So that's how that goes. So get the moment generating function, and then you can keep getting all the moments from that. That's why it is called a moment generating function. It keeps generating the moments. So important properties of moment generating functions. Property 1, it is uniqueness. So if two random variables have the same MGF, then they have the same probability distribution. So property 2, sum of independent variables. If x and y are independent random variables, then m sub x plus y of t is m sub x of t plus m sub y of t. This property makes MGFs very useful for studying sums of random variables. So you have this example with Poisson variables. Let x1 and x2, you have two different variables that follow Poisson distribution with parameter lambda. So the MGF of each variable is m sub x of t equals exponential, that's e raised power lambda into e raised power t minus 1. So for the sum, you have x1 plus m x2. So in that case now, you have m sub x1 plus x2 of t, and that's simply mx sub t all squared. So that means when you square this expression, it's exponential. So the 2 just multiplies it. So you have exponential of 2 lambda e raised power t minus 1. And then therefore x plus 1 plus x2 follows Poisson process with parameter 2 lambda. So table of common MGFs now. So some common MGFs we need to be familiar with. So for Bernoulli, which we found already, the moment generating function is mx of t equals 1 minus p plus p e raised by t. So if you want to generate, so with this moment generating function, now you can find the mean, you can find the variance by looking for the first moment, which is the mean coincidentally. Then you get the second moment, which is the expression of x squared, which you can then use to get the variance. So you can do that for each one. So for binomial, we have this like this. For Poisson, we got this. For exponential, we also already got this. For normal distribution, we have this also like that. So we can also do some Python simulation example. So we can approximate the MGF using simulation. So the MGF definition is m sub x of t equals expectation of e raised power tx. So the expectation can be approximated by the sample mean, and we just set up this kind of situation, right? And So we set the parameter to lambda to be 3, and we do a random Poisson kind of process for 100,000 trials, and then we get this kind of thing. As t is increasing, we also have the mx of t increasing. I always like my mx of t to appear like it's LaTeX, so I use $ to make that happen. So then I will run and see it looking a bit cuter than what it was before. So let's look at some applications of MGFs. MGFs are used in many areas of probability and statistics. Finding moments of distributions, for instance, like what we've just done, identifying distributions, studying sums of independent random variables, proving limit theorems, statistical inference, and theoretical statistics. They are usually useful when working with families of distributions, right? Like we've shown some popular ones like Bernoulli, binomial, Poisson, exponential, and of course normal distributions. So look at the problems. You want to try them out based on the things we've been doing. So solve the following problems related to moment generating functions, MGFs. Assume that the MGF exists wherever needed. So let X be a Bernoulli random variable with parameter P. Find the moment generating function mx of t. We already did that before. Use the MGF for Bernoulli distribution, compute the mean, compute variance. We've done all of this. So just I'll just flash through them. And so if you need any more to confirm, we already have a list of these generating functions, and we did some of them also. Okay, so you want to try your hands on them and be sure you get the gist. Let me know how helpful this is for you. Okay. And let me know how full it is. And if there's something else you let me to try out, feel very free to let me know. This is a very nice example. You have mx of t equals 1 over 1 minus 2t. It just looks like the lambda over lambda minus t thing I did. So you can use this to find the mean and the variance. Differentiate, evaluate at 0, you get the mean. Differentiate the second time, evaluate at 0, you get expression of x squared, which you can then use to get the variance. So with this, I come to the end of this. Let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. Don't forget, I have a whole playlist on generating functions, which you can interact with on my channel, right? Ultimately, uh, don't forget to comment, like, share so that more people can have access to the great content I have going on here. If you have not subscribed already, this is a very good time to subscribe. And you can also become a member of the channel by clicking on join. And that gives you special privileges, like getting to see some videos first, being the only one to see some videos, and of course, requesting for PDF copies of my notes. We can also hang out to discuss about things that interest you on my channel. Until I see you again, keep doing maths right. Bye.